Over further review. We're going to start at the very beginning, the very first chapter that I was asked questions about, and we're going to go chapter by chapter. First question I was asked was chapter 29, number 19. Something that drives me crazy about this app, you open it up and you turn on the template, and the default marker is black, even if you choose a black background. So if you look, every time I open this up, I always start writing. If you look really, really close, you can see a black tube. I can't see it. So I got to remember, I got to switch it to white because we're racist. And I'll do chapter 29, number 19. Okay. Number 19 gives us the electric field of a long straight line charge with lambda coulombs per meter is equal to this. So E equals 1 over 2 times pi times epsilon naught times lambda divided by r. Suppose that we move this line of charge parallel to itself at speed v. The moving line charge constitutes an electric current. What is the magnitude of the current? So what's the current of this moving line charge? So part A, we need to know what line charge is. So a line charge, typically we define that as lambda. Lambda, we see is in this equation, and lambda is equal to the charge per unit length. I'm asked to find the current. To find the current, I need to know what current is. What is the definition of current? So we got to remember back from previous chapters, the definition of current is that Nate should not be late. Should I let him in?
No. He commutes. Send him home.
He commutes? Yeah. You commute?
Send him home.
I don't have a car also.
It was a flood, wasn't it?
No.
Yeah. What? There was a flood, yes?
It was not having a car.
There was a flood, yes?
Yeah. That too, yeah.
Flood waters. Yes.
You don't walk through the flood.
So we have current. Current is equal to dq over dt. That is the definition of current. Okay?
She lives next to me and there's a flood. There's a flood between D1 and D2.
Yeah?
Oh, yeah.
Flooding,
That's
right?
why we were late.
Flooding.
I thought it was a flood in this class.
Horrible floods. There's flooding in this classroom? I'll clear it out. I'm a physicist. I'd fix it. Okay? I is dq dt. So these are definitions. Both of these, that's previous chapters. Is it fair to ask you about previous chapters?
No.
Absolutely. In fact, I could take this problem and I could make it a 20-point problem by making you derive this.
Ooh. Just don't.
Which we have done.
Well, you wrote the exam. Have you done that? Did you do that?
Maybe. Okay. So you would go back to chapter 24 to figure out how to do that.
No.
Yes, you would. That's where you would go. So if I wanted to find the current in terms of the line charge, I need to take the derivative of Q in terms of the line charge. So I need to solve this for Q. Q is equal to lambda times L. How did I get that? Algebra. I just multiplied both sides by L. That moves the L over to the left-hand side. Q is equal to lambda times L.
Are we deriving it right now?
We're deriving some stuff. We're not deriving this equation. We will not derive this equation in here. I've done it before.
But you're going to ask us on the test.
Maybe. Who knows? Okay, I can take the derivative of this. So I need to do dq dt. If I take the derivative of this, that gives me the current. So I need to take the derivative with respect to time of lambda times L. I have to know further. What is the derivative of both these things? If I take this derivative, what rule do I have to follow? This is derivative of two things that are multiplied together. That's the product rule. Product rule says the first variable, lambda, times the derivative of the second, plus the second variable times the derivative of the first. And then you have to do yeah, and you have to do jazz hands. Shaking back and forth. Deformed jazz hands, but jazz hands. We can simplify this. Lambda. Lambda is the line charge. Lambda is line charge spread out evenly. Lambda does not change. So what's d lambda dt if lambda does not change? Derivative of something is how it changes. If it doesn't change, what's the derivative of something that doesn't change? You can't hear on YouTube, but they all said 0 because I'm such a good teacher. Okay. A derivative tells you how much something changes. If something doesn't change, its derivative is 0. What's the derivative of 2? 0. It doesn't change. Because of the definition of what lambda is. Lambda is a line charge. It's how charge is spread out on a line. Doesn't change. Unless they were to give you an equation for it. They didn't give us an equation, so it's not changing. So this means that my current, I, is equal to lambda times dl dt. That is a change in position divided by a change in time. What's that also called? That's velocity. I is equal to lambda times v. Super, super simple answer, but getting there, not super, super simple. Why is that not super simple to get there? You're not physicists and you don't remember all the previous chapters. This is chapter 24, this is chapter 22, this is chapter 23, I think. This is chapter 3. So this is all prior knowledge. This is a prereq. Be good for a comprehensive final exam. Okay, let's do part B now. Part B says,
Bless you.
what is the magnitude of the magnetic field produced by this current? And you show that the magnitude of the magnetic field is proportional to the magnitude of the electric field. That is, they give you this expression. So we have to find what's the magnetic field. Well, magnetic field of a long straight wire, we already know what that is. What's the magnetic field of a long straight wire? We should know this one. Mu naught I over 2 pi r. Okay. I can further simplify this. I can plug in what I just solved for I. I get mu naught times I, which is lambda times v, divided by 2 times pi times r. In the problem itself, they ask us to prove that B is equal to mu naught times epsilon naught times V times E. So I have to somehow prove that these two are the same.
Oh.
Bless you. Flooding. How do I prove that? What do I have already? So I need to get a mu naught. Do I have a mu naught? I have a mu naught in both of these. Epsilon naught, I don't have an epsilon naught. Do I have a V? Yeah. I have a V right here. Do I have a big E? I don't have a big E. So I need to figure out how to get big E in there. I can get big E in there through lambda. I know that E is equal to 1 over 2 pi epsilon naught times lambda over r. I can solve this for lambda. So get lambda by itself. Lambda is equal to E times 2 times pi times epsilon naught times r. Plug that in for your lambda. And this is what physics is like at most state schools. Just plugging and chugging equations into different places. And if you could do that, they'd call you a good physicist. Does this make you a good physicist? Means you're good at algebra. That's all it means. This is an algebra problem. So I'm going to plug in my lambda. So instead of lambda, I have E times 2 times pi times epsilon naught times r. And then I have my V still, all divided by 2 times pi times r. The only thing I did there, I took my magnetic field equation, mu naught I over 2 pi r, plugged in the I that I solved in part A, which was lambda times V, and then I took the equation that they gave us at the very beginning, solved it for lambda, and plugged that in for lambda to get this. So there's lots of plugging and chugging things into different places. It's just a big puzzle. How to know to do that? Well, after you see it done, you know how to do it afterwards. Kind of a pain. Can anything cancel? What cancels out? 2 pi r up top and down at the bottom cancel out. So then I end up with mu naught times E times epsilon naught times V. Is that what I want? Yes. I got mu naught, E, epsilon naught, V, V. So I just proved it. These problems are deceptive. These problems are deceptive because they actually give you the answer in the problem. That was always a red flag when I was doing those. Like, that's not a good sign. They told me what I'm supposed to get. That means it must be hard. Is this hard?
Yes.
No.
Yes.
This would never be considered hard.
Then I guess it shouldn't be on the test.
It's just algebra. Okay? All right. That's all the questions that I had on chapter 29. I didn't get, what? No, I got a question on chapter 30. Chapter 30. Let's see. Circular motion in a uniform magnetic field. So the particular question I got, I actually solved on video multiple times, so I'm not going to go over that one again. You can go find that on video. But I did get asked about how to do magnetic torque. Okay. So magnetic torque. I was writing a lecture, and I was talking to my girlfriend, and I was asking her for an example of magnetic torque. Here's the example that she gave me. She always says that I'm the funny one, and she's not the fun. Or I always say that I'm the funny one, and she's not the funny one. Is she the funny one? Based on that, is that fun? Miley Cyrus in an MRI. How is that magnetic torque?
Oh, because it's a force in a magnetic field.
It's what would Miley Cyrus do in an MRI?
I don't know, she's calmed down a bit these days.
Twerking in a magnetic field. Okay. Now to do an example. No, I'm not going to twerk in a magnetic field. Let's show you what this kind of looks like and how we figure this out. So figuring out torque. So let's draw a magnetic field and draw a magnetic field going into the board. I'm going to draw a wire loop in this magnetic field. And I'm going to draw some currents going around. And you use these currents to figure out what direction the magnetic force will go on the different segments of this loop. So to figure out the direction that the force goes, I need to take my fingers and I need to point them in the direction of I need to bend them in the direction of B, and then my thumb gives me the direction of F. And I need to figure out if there's going to be any torque, any rotation on this wire loop inside of this magnetic field. So if I take my fingers and I put them in the direction of I, let's do the top wire. Top, I take my fingers, point them to the right. I bend my fingers in the direction of the magnetic field. My thumb gives me the direction that the magnetic force would act on this. That's going to pull it up. Is that going to cause rotation? If I'm pulling this thing up. If I have a sheet of paper, here's my sheet of paper, here's my current going around, I have a magnetic field going into the board, I take this sheet of paper and I pull it up. Is that rotating? No, it's just translating. Is there any torque on this? Not on that wire. Okay, let's look at this one. How about this? What direction does this one go? So it's going down. I bend my fingers into the or out of the board. So I need need to rotate my hand around so I'm bending into the board. What direction is my thumb going? My thumb is going to the right, so my thumb's going over here. Is that going to cause any torque? So here's my paper. Here's my magnetic field all going into the board. I take my sheet of paper and I pull it to the right. Is that rotating? Nothing's rotating. So is there any torque in this example? No. So this is not Molly Cyrus in a magnetic field. This is Dr. B in a magnetic field. I don't torque. Those on YouTube can't see this. I have no butt to be able to torque. So let's do a magnetic field. Let's do another example.
The fingers bend in the same direction as the magnetic field.
We'll show you what torque actually looks like. And now I'm going to take this loop. I'm going to draw it, but I'm going to kind of draw it kind of angled. I'm trying to draw in 3D. This might be hard to see or hard to tell what's going on. But that sheet is lying perpendicular to the magnetic field. So if this TV screen is the magnetic field, this sheet of paper now is laying like this. So it's coming out towards you. Does that make sense? Okay, let's draw the current that's going through this. So let's say I have some current up here at the top going this way. Yep. So I'm going to take my hand. There we go. Take my sheet of paper. Take my hand. My hand's going this way. Yeah. What direction do I bend my fingers? Into the board. So I rotate my hand 90 degrees so I can bend into the board. What direction is my thumb going? My thumb's going up. So this back piece is going to feel a force that's going up. And that means I'm taking this sheet of paper and I'm pulling up on this side. Is that rotating?
Yeah.
Potentially.
Right.
Now, if I take the bottom piece, so this front part of the sheet of paper, if I move this down, that means I'm going to rotate, right? If I move it up, though, then I'm not rotating. So I need to figure out what direction that force is going to. So that's figuring out the direction of the force on the bottom. Okay. So let's take my sheet of paper again. And now I gotta bend my fingers. My fingers going that way. I bend my fingers into the board. What direction is my thumb going? Down. So the front of the paper is being pushed down. I'm pushing the front of the paper down, the back of the paper up. I'm gonna rotate. Yeah? So if this goes down, then I'm going to get some rotation. Rotation is going to rotate around the center of the sheet of paper, and it's going to kind of rotate around. Huh? Yes?
So why doesn't the first one rotate? Because it would be having the...
First one, the way the forces end up going, if the top of the paper I'm going to be pulling up, the side of the paper I'm going to be pulling right. The other side of the paper, I'm pulling this way, I'm pulling down. So there's nothing to spin it. It's the difference in the orientation of the paper.
Okay.
This orientation versus this orientation. And I use that to determine what direction the forces are going to make it rotate. The angle I'm not so concerned about, figuring out the angle. It's something in between those. If we know rotation, yes, and rotation, no, we can figure that out. That's torque. Okay?
So you just need two sides opposing.
Yeah.
They do all
Okay.
So this is like the magnetic, like sort of the idea of like the magnetic motor, right?
Yeah.
How it works.
This is magnetic motor. This is you did this in lab to get magnetic torque for spinning motors, or you should have. And you probably all hated it.
Yeah. Very lame.
Joe told me you hated it. You said it was lame? That's not lame. That's how we get electricity. All right. Any other questions on the magnetic torque? Nothing else on magnetic torque? Okay. Other questions that I was asked? Everybody have a good weekend? Anybody do anything exciting? Yeah? You're going to beat me?
Oh,
What'd you do?
Well, unlike you being somewhere cold and disgusting, I was outside at the soccer matsu. It was really
the what?
The cherry blossom dust.
What's that?
Cherry blossom dust.
Oh,
That's what it's called.
that's a tourist trap. That's
No,
not
it's
cool.
not.
I was in Buffalo, much cooler than the
Cold,
cherry
wet,
blossoms.
disgusting.
Like I said, cooler. It wasn't wet, it was icy.
Yo, I ate some good food. Right, Wayne?
Wow, we degenerate pretty quickly.
What?
Degenerated pretty quickly in here. Okay.
Oh, wait, Dr. Bizarre, I have a question.
Nope, we're going to keep going.
We are.
I was asked about chapter 31 to do problem number 18, where we have a circular loop of wire that's placed in a magnetic field of 0.3 Teslas, while the free ends of the wire are attached to a 15 ohm resistor as shown in the following figure. When you squeeze the loop, the area of the loop is reduced at a constant rate from 200 to 100 centimeters squared in 0.02 seconds. What are the magnitude and direction of the current in the resistor? So we have to draw a picture, a little bit complicated of a picture. This is chapter 31, problem 18. Electromagnetic induction. So we have a magnetic field that looks like this. We have a little loop that we have inside of this magnetic field attached to a rectangular wire. I'm even color coding it exactly like the book, because I care.
The X's mean it's going into.
Yes, the X's mean that that magnetic field is going entirely into the board. So let's do number 18. Magnitude and direction of the current inside of this resistor. So to figure out the current in here, I need to use Ohm's law. Ohm's law tells us V is equal to I times R. And what I'm doing in this example is I'm squeezing this loop to change the area. Because I'm changing the area, that means I'm changing the amount of loop that's inside of a magnetic field. If I'm changing the magnetic field inside of this loop, I'm causing induction. If I'm inducing something, then I'm inducing current. And the normal thing we talk about with induction is induced EMF. So we're inducing EMF. Inducing some voltage is the current times the resistance. So the current that I'm inducing is the EMF that I induce divided by the resistance. I have a resistor in this problem. How big is my resistor? So I already know what the resistance is. Whatever the EMF is divided by 15 ohms is the resistance. So now I need to find the EMF. How do I find EMF? EMF. EMF is defined as d phi over dt. What is phi? Negative d phi dt.
Magnetic field times the area.
Okay, so I need to do d dt, phi, which is magnetic field times area. Is the magnetic field changing?
Did they say
Bless you.
that the current was changing?
They did not say that the magnetic field is changing. So magnetic field can come outside of this derivative, and then I only need to know how is the area of this changing.
Bless you.
Bless you. Oh my God. Breathe.
It's the devil.
So EMF, negative B. They give us that our magnetic field is equal to 0.3 Tesla. And then I need the change in the area divided by the change in time. They tell us the area of the loop is reduced at a constant rate from 200 to 100 square centimeters. So if I'm changing the area of this from 200 to 100. So I need to do the final minus the initial. What's the final size? 100 square centimeters minus 200 square centimeters. And then I need to divide by what? The time. And they tell us that it changes, the loop changes in 0.02 seconds. So I don't actually have to take any derivatives. If they give us an equation, we need to take a derivative. They gave us the rate of change. They gave us dA over dt. dA is the change in the area, which is the final area of 100 square centimeters minus 200 square centimeters, and then divided by dt, that's the change in time of 0.02 seconds. What's the problem in this? The way I've written it. Will you get this problem right? You will be off by a couple factors of 10. Why? Area is in centimeters. So you need to convert this to meters squared. Okay. So if you do all your conversions out, you'll get an EMF that's equal to 0.15 volts. So then your current is your EMF divided by your resistance. 0.15 volts divided by 15 ohms. Gives me my final current, 0.01 amps. That is the induction that you are inducing. The current that you're inducing. Okay. It also wants to know what is the direction that this current is going to flow. So I'm taking this wire loop and I'm decreasing its size. It's going to get smaller. So what happens to the magnetic field inside of that loop? I'm going to go from this big magnetic field down to this smaller one. So my loop's going to start looking like this. Let me try to draw one more X in there. So initially, how many magnetic fields do I start out with inside of this loop? Inside of the red loop, how many magnetic fields? Got 1, 2, 3, 4, and then 5. Right? So I start with 5. I decrease the size of my loop. How many magnetic fields do I have now? 1. Am I happy with that? No, I need to induce more magnetic fields. How many magnetic fields do I need to reduce? According to this picture, 4 more. And what direction do I want them to go? I want them to go into the board. So I need to induce some current so that I get these 4 lines. What direction does that current go? Does it go clockwise or counterclockwise? What do you want to guess? Gonna guess clockwise? Okay, if we guess clockwise, then I'm over here on the right side of the loop. That would mean I'm going down. So I take my thumb's going down. I want over towards the left of the loop. So I point my fingers towards the left. I bend my fingers, they're going in. So clockwise was the right answer. If that wouldn't have been right, what would I have done? The opposite way. And the opposite way would be the right answer. Okay? So I need to be going clockwise for that induced current. Do you have questions on number 18? Yes? I can. So if we want to, we want to figure out how to get these magnetic fields going in, yeah? So we're clear on that. I'm going to assume it's going clockwise, which would mean over on that right side of the wire, the current's going down. So I take my thumb and I put that in the direction of the current. And then I take my fingers and I point them where I want the current. Where I want the magnetic field. I want it on the left side of that particular piece of the wire. So I point my fingers to the left. I bend my fingers. They're going into the board. So that was induction and using Lenz's law. Yeah, questions? Any other questions? No? All right, that was number 18. Also got asked how to do number 29. How do we do 29? Chapter 31, number 29. Number 29, we have a rectangular loop, that measures 20 centimeters by 80 centimeters, and it's made of heavy copper wire of radius 0.13 centimeters. Suppose you shove this loop short side first at a speed of 0.4 meters per second into a magnetic field of 5 times 10 to the negative 2 Tesla. The rectangle is face on to the magnetic field, and the trailing short side remains outside the magnetic field. See the following figure. What induced current will flow around the loop? So I have a magnetic field. Again. When you become doctors, you will not have to do any of this, but medical physicists will do all this for you, because this is all important for all the equipment that you'll be using. You don't want to induce currents inside of your patients that will kill them. That would be bad. It's the same concept as shoving somebody into an MRI, which you don't want to do. So we have this loop, and I'm going to take this loop, and I'm pulling it, what direction am I pulling it? Into a magnetic field. So I'm pulling this loop this way at a velocity of, what's my velocity? 0.4 meters per second. My loop has dimensions. The width of this loop is 80 centimeters. The height of this loop is 20 centimeters. What would be a good idea at the very beginning of this problem? Change it to meters. Yeah. So that'd be 0.8 meters and 0.2 meters. Okay, what induced current will flow around the loop? When we were finding induced current in the other problem, we used Ohm's law. Induction, induced EMF is equal to I times R. Ohm's law, V equals I times R. If I can find the EMF that's induced, I can find the current if I know the resistance. So the induced current is the induced EMF divided by the resistance in this wire. There's a couple keywords that they give you that to kind of tell you how to find the resistance. They tell you that this wire is made out of copper, and they give you the radius of the wire. So that leads you to the equation for resistance, rho times L divided by A. This goes back to chapter like 26, I think. So that requires knowing that chapter. What things would I be giving to you? I would give you rho. Rho is called the resistivity of the wire. It depends on the material that you make your wire out of. This one's made out of copper. The resistivity of copper is 1.7 times 10 to the negative 8. Then we have to multiply this by the length of the wire. So the amount of wire that this current is actually going to be traveling around it. Resistance adds up. As you get a longer and longer wire, you're going to have more and more resistance. It builds up as your current is traveling farther and farther. So how long is this wire? So I have to imagine that I could take this wire and I could unwrap it. So I need to find the total perimeter of the wire, all the way around the wire. Basically the circumference of the wire, if this were a circular shape. So how do I get the total distance all the way around the wire? 0.8 plus 0.2 plus another 0.8 plus another 0.2. What's that? That's 2. So the total length of this wire is 2. And then I need to divide by the area. And that is the cross-sectional area of the wire. So wire is usually a cylinder, right? So the cylinder kind of wraps around. The cross-section of that wire is the circle shape of the wire. If I take it and take a cross-section of that. So what's the area of this? Pi r squared. 2 pi r would be circumference. Pi r squared is the area. So we do pi times the radius squared. And they tell us that the radius of this wire in the problem is, where'd it go? Is 0.13 centimeters. So that's 0.0013 meters squared. Plug all your numbers in. You'll get the resistance of 6.4 times 10 to the negative 3. What are the units? Ohms. Units of the monk. It's usually one of the very few jokes that you get in a physics class. Boom. Okay. What else do I need to find? I need EMF, because I'm taking the EMF divided by the resistance to get the current. What is EMF? Negative d phi dt. So negative d dt of B times A. Okay, is the magnetic field that this thing is sitting inside of changing? Is the strength, do they tell us anything about the magnetic field strength changing? In the problem itself, if you reread it, they are not changing the magnetic field strength at all. The magnetic field has a strength of 5.0 times 10 to the negative 2. So if it's not changing, what can I do with it? Pull it in front of the derivative. Negative B times d dt of A. Is the area of this loop changing? And by area, we mean, let's get really confused. This loop, I'm pulling it further into the magnetic field, right? So the amount of loop that's inside of there is getting different. It's changing. Is the height of the loop that's in there changing? No, still the same height. What's changing? The width. So I'm pulling more of the wire into the magnetic field, lengthwise. So I don't need to take the derivative of both parts of that. I have negative B times the height of the wire. We'll call that H. Okay. And the width of the wire, what do you want to call that? L? Okay. Over dt. Okay. What is dl dt? That's a change in position divided by a change in time. That's a velocity. That's how fast I'm pulling the wire. So this EMF that I'm inducing is equal to negative B times H times V. The magnetic field times the height of the loop times the velocity, how fast I'm pulling this. And they gave us all of those numbers. EMF is equal to negative 0.2 times 0.05 for the magnetic field times 0.4 for the velocity. Plug all your numbers in, you get the EMF is going to be equal to 4 times 10 to the negative 3. So I is the EMF over the resistance is 4 times 10 to the negative 3 divided by 6.4 times 10 to the negative 3 to get 0.63 amps. Okay. That's all that the problem asks. I might ask additional things. So what additional things could I ask? Let's draw a picture. Let's figure out where induction is going. I start off with this picture. We need to make that a little bit bigger. Then I come back a little bit later, and I've pulled my loop to the left, right? So I have more of the loop inside of this. So my loop goes from looking like this red one to looking more like this yellow one. Okay? So we'll call this top picture before, bottom picture is after. So what happens with induction? What's happening to my magnetic field? Is it increasing or decreasing? Increasing. I'm getting more magnetic field lines going into the board. So we're getting more negative magnetic fields. Higher negative magnetic field. Okay. So I'm getting more magnetic field lines going into the board. if I were to ask you, draw in green, what direction is the induced magnetic field going to go? What direction is the induced magnetic field going to go after? It's going to go into the board, which would be negative K, or out of the board?
Out of the board.
Out of the board. Positive K. Wants to come towards you to cancel out those two additional ones. So what direction does the current, induced current, have to go in this second loop? To go clockwise or counterclockwise? You're going to say counterclockwise?
Yes.
Let's guess counterclockwise. Counterclockwise means over here I'd be going up. So let's see if that's right. I take my thumb, put it in the direction that my current's going. I take my fingers, I point them over to the right because that's the relative location where I want the magnetic field. I bend my fingers, they're going out of the board. Is that what I want? Yeah, so induced current would be going out of the board. So that's the additional thing I could add on to this. What direction is the induced magnetic field? What direction is the induced current? Other things I could change, I could pull the loop the opposite way.
So that doesn't change anything.
If I pull it the opposite
Oh,
way,
it gets
that
less.
means I want more magnetic fields going into the board, so my current, induced current goes the opposite way.
Wait, can you repeat that part?
If I pull
Pull it
this
the
loop
opposite way.
the opposite way,
So you're pulling it that way.
I'm going from having 4 to only 2 lines inside
Yeah.
of the field.
Yeah.
I want to get back to 4, so I want 2 more lines
Yeah,
going
yeah,
in.
in. Yeah.
So then the magnetic current would be clockwise
Yeah.
to give me lines going in. Okay. Those are the ways that I would change that potential problem. Do we have questions on number 29 in chapter 31?
Oh.
So we wouldn't use the right-hand rule starting with the fingers, because that's for magnetic force.
That's for force. We're looking for fields.
Magnetic
Yeah.
direction.
Yeah. Nothing else there?
Wait, quick, just to recap, so the
Yeah.
induced current is coming out of the board, right? And then-
Induced magnetic field is coming out of the board.
Okay.
Induced current is going counterclockwise
Oh, I see.
to give you the magnetic field that comes out of the board. We've been pretty consistent with magnetic fields going into and out of the board. I will maintain that on the exam. I won't start giving you magnetic fields going left and right and currents going into and out of the board. It's the same process, same exact physics. But
You can ask
that would make your heads explode. So I won't do that because I don't want to clean it. What was that?
You can ask that in physics 3.
Yeah, if we ever offer it. We never will. I'd have to teach it. Nothing else from there? Okay, let's do chapter 34. A couple questions on this. Chapter 34, somebody wanted to see number 74. Chapter 34, number 74. So let's flip to that. They actually only wanted to see one part, but I think it's worth doing all the parts. There are 2 problems that are very similar, number 74 and 79. I did 79 in class, so I'm not going to do that one again. There's a video that you can watch for it. If I gave you something like number 79, I would give you it in a format more like 74. 74 walks you through all the steps and kind of explains everything. So you just have to know how to follow directions to do it. Hopefully we can all follow directions. I'm skeptical. Number 74, we have a picture with a light bulb. That's all your brains. When you're taking my exam, light bulbs going off or more likely burning out. And we have a lens. What kind of lens is this? Based on that picture. That's not concave, so it would be convex. That is a convex lens. And then we have a mirror. Okay? What kind of mirror is that? That is a concave mirror. Things I could do to this problem. I could change the mirror. I could make the mirror convex. I could change the lens. I could make the lens concave. I could change both of them. I could put the light bulb in between the two. There are infinite different ways that I can change these things. But it's all the same process. Always the same equation. Only one real equation that applies to these kinds of lens and mirror problems. What's the lens/mirror equation?
1 over S plus 1 over S prime.
1 over S plus 1 over S prime equals 1 over F. So that's all you're doing. You're just doing variations on that. Constantly doing different ways that I can orient things. Doing algebra on those three numbers. Okay? They give us some information. They tell us the concave lens has a focal length of 25 centimeters. So this focal length of the lens is 25. It's at a distance of 60 centimeters from a concave mirror of focal length 20. So this distance is 60 centimeters. And the focal length of the mirror is 20. Again, all these things are given. And the light bulb is 80 centimeters from the lens. So this light bulb to the lens is 80 centimeters. I have all these things in centimeters. Do I need to convert them into meters? No. As long as you leave everything in centimeters in these problems, you're fine just leaving them in centimeters. Can you convert them to meters? Yeah, sure. If you wanted to. But there's no reason. Other questions. If I change this to a diverging lens, but kept everything else the same, a concave lens, what would change?
The focal length
Focal length, what would change about it?
would become negative.
It'd be negative. How about if this was a convex mirror?
It would be negative.
It'd be a negative focal length. Okay? How do you know all those sign conventions?
Your cheat sheet.
Cheat sheet. Put that table on your cheat sheet. Put it on your cheat sheet and practice using the tables. Don't try to just scratch it out the night before. So part A asks us, where does the lens form an image of the light bulb? So we can ignore everything about the mirror. We just have the lens and we have the light bulb. So I apply the lens equation to that. Where do I get the image? 1 over S plus 1 over S prime equals 1 over F. I'm solving for the image distance. What one of those variables is the image distance? S prime. So I want to get S prime by itself. 1 over S prime equals 1 over F minus 1 over S. One over S prime equals 1 over F. What is F?
Focal length.
Focal length of what?
The lens.
The lens. Why?
That's what we're doing.
That's what they asked us. They said, where does the lens form an image of the light bulb? So we want to use focal length of the lens. Minus 1 over S. What's the object distance? How far from the light bulb to the lens? 80 centimeters. So 1 over S prime, plug and chug all your numbers in. You get 1 over 36. So S prime is 36 centimeters. So I should draw that in. Where is that going to form? Where is that image? Is it on the left side of the lens? On the same side as the object, or on the right side of the lens? What'd you say? What'd you say? I thought I heard you say. Maybe I just.
Is it convex or concave?
This is a converging lens. I got a positive image distance. Where do I expect a lens to focus an image? Behind the lens. So is that on the right side or the left? I'm going to be on the right side. I'm 36 centimeters over there. So I'm going to get my image. Let's draw our image. 36 centimeters over here. So there's my image. And part B. Where does the mirror form an image of the first image? What that is telling you is that mirror is going to completely ignore this light bulb. It's going to completely ignore this lens. And it assumes that this image is the object for the mirror. So I need to find how far it is from that yellow circle to the mirror. So the distance, the object distance for the mirror is equal to how far it is from the mirror to that image. How far is that? Well, I know
24.
from the mirror to the lens is 60. And I know this object, this image, is 36 centimeters to the right of that. So I need this distance. I do 60 minus 36 to get 24. Yep. I have 60. The whole distance from the mirror to the lens minus the 36 centimeters closer that the image is. And I get SM is 24. Oh, good. That's what I got on my notes, too. What if I would have done this? What if the math would have worked out and the image distance was negative?
Then it would be on the other side.
Then my image would be over here, and I would do 60 plus 36. Same exact procedure. You're doing the same physics, you're just doing it over and over again. So now I can plug and chug to get all my numbers. I'm looking for the mirror image now. We call it SM prime. Equals 1 over F, focal length of the mirror, minus 1 over SM, the object distance for the mirror. 1 over SM prime. 1 over FM. What focal length do I use? The lens or the mirror? The mirror. Because the mirror is making the image now. 1 over 20 minus 1 over 24. Plug and chug all your numbers in. You get SM prime is equal to 130. Now they ask us, what part? Where does the lens form the final image of the second image? So what that's telling you is this image, this SM prime, becomes the object for the lens again. So the lens is going to focus on that image to form the final image of the whole overall thing. Oh gosh, where is this thing? I got a positive 130. Am I on the left side of the mirror, the front side of the mirror, or the back side of the mirror? Front side. Why the front side? It's positive. If it was negative, I would be on the back side. So I'm 130 centimeters away from this mirror. This is my second image. We'll do our second image in green. So that is 130. Now, that second image, this green blob, becomes the object for the lens again. So I need to know the object distance. How far is it from this green blob to the lens?
Wait, shouldn't that green blob be on the other side of the like metal?
Well, 60 plus 80 is
Oh,
140.
just kidding. I can't add.
So this is about 10
Yeah.
centimeters. How do I get that distance?
What was your question?
How do I get this distance from the lens to the second image?
You subtract.
I have 130 here, minus this 60. That gives me the distance between the second image and the lens. So for the final part of this, I have the final object distance is 130 minus that 60. That gives me 70 centimeters to the left of the lens. Yeah? I'm now on the left of the lens. What does that mean? Closer to the bulb. What else does it mean? This is where things get a little funky. Because I'm to the left of the lens, the object distance is negative. Because I'm to the left of that lens. So now I have 1 over S prime, again, equals 1 over F minus 1 over S 1 over S prime. What focal length do I use? Lens. Minus 1 over negative 70. Plug and chug your numbers in. I get 18 centimeters. I get positive, so I'm 18 centimeters to the right of the lens. Okay. That is number 74. Every other question I was asked, I responded to it in the discussion board. Somebody asked for problem number 80, but problem 80 is a little bit confusing, and I don't think I actually assigned that one. If I did, I didn't mean to. So number 80 won't be on the exam. Something more like 74. The last question I asked was kind of more general, like S prime in terms of S and F. What does that actually mean? And this has to do kind of with the worksheets. And how would you solve a problem if you're given things in terms of what I was given on the worksheet? So let's say if I said S, the object distance, is equal to something like 3F. Object distance is equal to 3 times the focal length. Find the image distance. How do I do that? Well, what's the lens equation again? Let's again say this is a converging lens. So we know this is all positive stuff, makes it nice and easy. 1 over F equals 1 over S plus 1 over S prime. I ask you to find, what is the image distance? So solve the image distance. We've been doing this all along. 1 over S prime equals 1 over F minus 1 over S. Keep going. 1 over S prime equals 1 over F. And I tell you at the very beginning, 1 over that F is, or the S is equal to 3F. So I have 1 over F minus 1 over 3F. Do you see what I did there? Took the S that you were given, and I plug it in to get this. I keep going. 1 over S prime equals 3 over 3F minus 1 over 3F. What the fudge did I do there? I multiplied by 3 so I can get a common denominator. I can't just subtract 1 over F minus 1 over 3F. Subtraction of fractions, I need a common denominator. This goes way back. This is like elementary school. Middle school. Okay, so I have to do 3 over 3F minus 1 over 3F. I get, what do I get? 1 over S prime equals 3 minus 1 over 3F. 1 over S prime equals 2 over 3F. So S prime would be 3 times F over 2. No? Questions on that? Okay.